Okay, so welcome everybody. Hopefully everybody had a good lunch and you're wide awake. I will say this is one of my favorite presentations to give, so I hope to be high energy and keep you all awake for this next hour. So I'm going to talk a little bit about graph algorithms, how you can use those with Neo4j to predict real-world behavior. So just a bit of background on myself. I'm an engineer at Neo4j. I enjoy developing code, writing code, and then going out on the road, as well as writing technical blogs. I write as much as I can, and then whenever I can, I get out and speak. So I'm thrilled to be here at JFocus. I also love my cat's coffee and traveling. I'm sure my cats are waiting at home for me. They like to sleep in the chair in the office while I code. So I'm sure they're missing me this week, but they put me out on loan to you guys. So. Back in the 1940s, the U.S. Air Force had a problem. They had a lot of airplanes crash. In fact, they had up to 17 crash in a single day. Not very good statistics. Obviously, that's a problem. We need to fix this, right? So they started looking at what can we do, what's going wrong, and they kind of came up with, well, maybe the size of our pilots has changed. Maybe their arms are longer, maybe they're taller, maybe their hands are wider, and so the controls are a little bit differently set. So they took 4,000 pilots, they measured them, they took about 100 different dimensions, and then they looked at boiled them down to kind of 10 key factors. And they thought if we can measure and kind of find everybody who will fit within this 30% plus or minus of these averages, we'll be good to go again. We can redesign our cockpits, and we'll be off and running, no more crashes. What they actually found is when they started measuring their pilots, not a single pilot fit within that 30% plus or minus band. That very wide range of average, and they couldn't find anybody to fit that. So what they found was that averages will fail you. If you design for average, you design for nobody. We're going to talk a little bit today about 3 different areas of graph analytics. This will be different from the areas of graph algorithms we'll talk about in a bit, but just to look at kind of the 3 different focuses of graph algorithms. The first is propagation pathways. So it looks at how things move through a network. What are the routes something takes, and how does it go from point A to B? Next is the flow and dynamics. So how much is your capacity? What's the flow through? What's the volume? And figure out how things, traffic is going through. Then finally, we have interactions and resiliency. So this looks at the groupings of your data into different communities, and then how well they pull together, or how easily it is for them to break apart, and what causes them to do that. So in our story just a few minutes ago, we already saw that averages don't really fit reality. And actually, there's not a single network in nature that fits this average distribution, this random model. Now, this is a nice, pretty bell curve. Very mathematical, but what you actually find in nature is something more like, gotta point it at the correct thing, something more like that. It's a power law distribution. So it's kind of a scale-free network where you have a few nodes that have a ton of connections, and then the rest of your nodes have some connections, but not as many. So it's not just kind of this average distribution. For those of you who may do better visually or not with mathematical models, it looks something like that. So you have your random distribution there on the left-hand side. That doesn't even look visually acceptable. It doesn't look natural to any of us. And so the visualizations on the right-hand side, however, your scale-free network and then your small world network, those things are ones that you actually find in the real world, and they're much more natural to the eye. So the scale-free network is any data set size you're looking at. It has a very similar structure all the way up and down. So no matter how it scales, the structure looks very similar. The patterns look similar. The small world network you can see is this hub and spoke, very interconnected, kind of like a social network type of structure. So we can see this in practice. Here's some examples. The one all the way on the left-hand side is the human malaria parasite. Some studies on that and how some of the genes break and separate there. In the middle is a species hierarchy, so it's looking at species that fall into different categories within a hierarchy. And then all the way on the right-hand side is looking at a somewhat unknown data set and then trying to predict missing information in that data set. So it's looking at the impact analysis, what could be missing, what are the possible missing links, because I have these other links in places, and this pattern is also similar. So we can use these types of things to understand the world around us, and then to predict what something might do or a path it might take. So you guys may have seen on social media some of those little like eye tests or whatever, where it asks you, X plus banana equals this, and then it uses banana and all these little things and says, okay, what's the value of the banana? Or they'll give you a pattern like red, yellow, red, and then yellow, red, yellow, and then ask you what's the next pattern. And of course, all of us kind of take those patterns and we automatically fill in the blanks. Or we're able to construct an answer based on the patterns that we've seen before. So this is exactly what this does, just at a more complex scale. So now we're going to look at 3 areas of graph algorithms. Remember I said don't get confused. This is not the exact same as graph analytics problems. These are just different areas of graph algorithms. So the first is pathfinding and search. This looks at the optimal route through the network. What is my shortest path? What's my most efficient or highest quality? Or what's the best route to take through the network? Next, we start looking at importance of nodes. What are my bridge nodes? What's the best way to get information around? What are the nodes that help me kind of move things through the network that are high importance? And then finally, community detection. So how does my data kind of group together? How does it tear apart? And what kind of mapping structure does that group analysis look like? So we're going to look at some algorithms in each one of these areas really quickly. First, in our pathfinding and search, we have single source shortest path and all pairs shortest path. Those are harder to say than what they look. Single source starts from, for lack of a better term, a single source, so a single root, location, node, et cetera, in your data set, and then looks at the shortest path through the network from that node, always going back to that node, so hence single source. All pairs shortest path, however, looks at the shortest paths between all the nodes. So it's looking at multiple shortest paths. So single source shortest path, see, told you it was hard, looks at, so it can be used for things like routing, so like GPS, and looking at how do I get from point A to point B. And so that's good at telling you your best path, your optimal path through the network. And that could be based on anything. It could be based on use highways, it could be based on use toll roads, it could be based on get me the shortest mileage or get me there the fastest, et cetera. Where all pairs looks at alternate routes. So it looks at all the other routes if your optimal route is taken up. Here's a good example of this. This is call routing in a telecom network. So in this case, they're using least cost routing. So they're looking at what is the lowest cost I can get a call from one end of the network to the other. And so depending on what if your optimal path goes down, what if a node there goes down, how can I reroute that? So that would be your all pairs there, and then your single source would be the initial take through that network. Minimum weight spanning tree looks at the path with the smallest value for visiting all the nodes. So this is kind of like a delivery service, if you can think of mail or trash and recycling. They have to visit each and every house, but they have to figure out what is the most efficient way to visit all the houses in the neighborhood each week, or in the city, et cetera, however wide the route might be. So that's used a lot for that. And then finally, we have parallel breadth first search and depth first search. Those are also very hard to say. Breadth first search looks at a particular point and then traverses the network from your nearest neighbors out. So it starts very close to you and goes, okay, what's my next nearest? What's my next nearest? So you can think of this like, what are the coffee shops near me? It starts at you and starts at your little pinpoint and then goes, what's closest to me? Okay, what's the next closest? What's the next closest? And it keeps surveying that area around. So that's breadth first. Then depth first actually takes a single point down through the graph before it comes back up. So this is used a lot in video game simulations, where you could look at a character, if I take this particular path, then is my traversal all the way down to win the game? Or if my character takes this path, then what's the traversal all the way down the tree to win the game? So it always goes all the way down the tree through the end of the graph first, and then it comes back up and does it down another tree. Next are centrality algorithms. PageRank is probably the most popular, the most common. And it was made famous by Google using their search engine. But there's a lot of other cases for it as well. But it basically looks at what nodes have the most overall influence. Now, this one can be kind of tricky between this PageRank and between a Centrality, because they both look at influence. But we'll get into kind of the details of which one does what exactly in just a bit. But some other use cases that PageRank is used for, so urban planning and development, they apply it to that, as well as tracking extinctions. So what extinction of what species would cause the most impact for mass extinction of several species. And then finally, it's being used to fight toxic waste. I don't know why it just double-clicked on that. That's odd. No, stop. Okay, there we go. It apparently took its own control. So it's being used to fight toxic waste. A little anticlimactic there, but I don't know exactly how they're using PageRank to fight toxic waste, but it's still a pretty interesting use case, nonetheless. Closeness centrality looks at which nodes are able to reach the entire group the fastest. So if you're wanting to disseminate a lot of information very, very quickly, you would try to find somebody who has a very close arm's reach to the most people. So in this case, Alice is probably your best bet. She's a single hop from most everybody, except for Michael up there in the corner. You have to jump through Charlie, but still she's able to reach most the fastest over anybody else. So you can imagine if you were trying to plan a new transportation hub, or a hospital, or a police station, you would want to figure out what's the closest where you could get to a bus stop, or a grocery store, or a bank, or hospital, or what have you. So you would want to run something like this to figure out what's the best location for this, where they could reach the entire city and serve the entire city. Between a centrality, so I mentioned this one and PageRank are somewhat similar, so it looks at which nodes are the bridges between different clusters. So it does look at influence, but it looks at how these nodes connect to other groups of nodes. So you may have some little communities here and there, and then you have these kind of central nodes that might be able to bridge some of those communities and those groups. This particular example here, the company was having issues pushing through some communications throughout their company. Some were getting through, some were not. What they actually found when they did analysis is that this orange node here in the center, that was a QA person who actually was going around to each of the buildings manually and working on systems and talking to people. So he was actually kind of pushing this information across throughout the company because he was visiting all these buildings. And then the buildings he didn't visit obviously didn't get the information. So you can see if you wanted to put a message out there and get it through this network, you would want to go talk to him and you want to push it through him. However, if you would want to fix the actual communication problem, then you might ought to figure out how to go around him and still get to everybody as well. Then finally, degree centrality. So this is looking at the number of connections in and out of a node. This is actually trying to figure out how fast a disease would spread through a particular person or how fast a person could get a disease. So if you look at, this person, the example that kind of comes to mind automatically is gossip. How fast will gossip travel? So you look at, okay, who tends to tell to everybody. So if the information gets to them, you're probably in trouble. It's going to get out really fast. But if the information gets to this other person, they only might talk to a few people, so you might not get out as quickly. But it's also used for looking at disease. So this is using centrality. So on the left-hand side here, we're going to do a random removal of nodes. We're just going to start removing random nodes out of the network. On the right-hand side here, we're going to look at influence. So we're going to pull the highest centrality nodes. We're going to start taking those out of the network. And as we kind of move through this, you'll start seeing very quickly that the influence removal is tearing down that network far faster. And just after 19 moves here, you can see that the one on the left-hand side, that network's pretty much still intact. It's still functioning, there's information still flowing, there's centers of control in the larger nodes, everything's still good there. Where on the right-hand side, that network's pretty much destroyed. So you can see how much of a difference this would make if you're looking at targeting cells for cancer, the diseases, go after the most important and the control centers, the brains of those diseases, and target those cells first. Also really important for things like terrorist cells and terrorist networks. You can start breaking down those networks very quickly and disseminate all the resources. So very important. Another good example is this electrical grid. So in Europe, here in Italy, obviously, they were seeing cascading failures throughout an electrical network. And so, the company does analysis. What do typical companies do when you start having cascading failures? Contingencies, bolster it up, add more backups in there. So when you have one go down, you have these failovers that kind of take their place and they reinforce the network. However, they started doing graph analysis, and what they found is that they could prevent their cascading failures by removing nodes. They took out 4 nodes in their system, and all of a sudden those cascading failures at least slowed down, if not stopped. So what was happening is that those nodes going down would then propagate and spread like a disease to other nodes, and then those would go down, and then it would continue on further, causing more failures. Okay, last segment here on community detection. Label propagation is a good first pass through your network. So it's used a lot. It's not end-all, be-all, but it's a good idea if you want to kind of just get an idea for how your data structure is kind of organized into different groups. This is a good one to run first. It basically spreads labels based on the neighbors to infer the different clusters. So for instance, if you were to take me and all of my friends happen to be music lovers, then you might also assume that I could probably be a music lover. If all of my friends around me were music lovers, hey, she probably likes music, or she probably wouldn't be friends with all these other music people. So it kind of does that basically through the entire graph. Makes some assumptions, not always probably accurate, but it's definitely a good first pass. And then we have union find or weakly connected components, and then strongly connected components. So weakly connected components looks at groups of nodes that all have a path to each other, but it doesn't mind the direction. So in this particular case, we have weakly connected components. You can get to every other node if you ignore the direction of the arrows. Whereas strongly connected components finds groups that are all connected to each other when you follow the direction of the arrows. So in this case, we have Bridget, Michael, and Alice here, that following those directions, you can get to any of the other nodes from there. So I like to think of this like one-way or two-way streets. If you were to ignore all the one-way streets, you could probably get to a lot of different places pretty easily. But if you started following one-way streets, then it might take you some extra hops to get all the way around, or you might not be able to get to certain places without following those. So, Louvain modularity. So this looks at the presumed accuracy of a grouping. This one is really interesting because it starts looking at how things, density of your relationships within groups. So on the right-hand side there, you can kind of see this example. I'll talk more about it in a second. But it starts looking at where my groupings of all the relationships will group these people together, and then what's kind of the outlier then at that point. This one can, depending on your data size and the number of times you run it, some results can change. What it basically does is it groups different nodes, and it keeps moving nodes around until it finds a good weighted grouping of things. So the more you keep running it, sometimes if you have certain nodes that don't quite fit in certain groups, and it just continues to go on and on. But still, it does a really nice job at detecting fraud rings because it's looking at what are all the relationship densities, even seemingly unrelated networks, supposedly random networks. It analyzes them and says, these kind of are outliers. You might want to check out these two nodes because they might be a fraud ring. They might be connected, even though they don't look like they're connected. So in this example here on the right-hand side, we have another telecom network, but it's French and Dutch speakers, telephone, across the telephone. So you can see that most of the time, those two groups kind of stick to themselves. French talk to French, Dutch talk to Dutch. But then there's this little group in the center. It's kind of exploded out where you see cross-pollination there. You have some people on one side talking to the other and vice versa. So if you were wanting to strengthen this and strengthen the bond between French and Dutch speakers, you would kind of target that group and try to expand it and grow it. Conversely, if you were trying to break that apart, you would also target that center group. Finally, we have triangle count and clustering coefficient. This is also used by epidemiologists to look at the spread of diseases. But it's just looking at the degree that nodes tend to cluster together, how strong those interactions are, what would cause them to break apart, what would cause them to stay together. So we already know that algorithms are used in a lot of different use cases. We've already just seen several, but this is just the beginning. Whoa. Back. Having trouble with the clicker today. But there's a ton of other use cases where graph algorithms are being explored or being utilized. And there's tons more analysis that could be done in this area. So I like this quote from Steven Scianna here that basically says if programmers can start using this analysis and this knowledge and analyzing these patterns, you could really become quite powerful and quite knowledgeable about the systems you're dealing with and about the data you're working with. So what inspired Neo4j to break into the space, besides for something like that? So there were some processes that existed out there. This is one of them by a community member that basically took the Twitter streaming API, piped it through this process out to Tableau and a graph visualization. So Neo4j is sitting there in the middle, but you can see that there's a lot of technology ground covered. A lot of different technologies, a lot of things that developers would have to do that they may not be completely comfortable with. And so our goal was to kind of streamline this process, make it a little bit simpler, see if we could make the developers' lives a little easier, and kind of just put that together just a bit. There we go. I figured I would get warm while it was up here. So how do you actually go about accessing graph algorithms with Neo4j and running them? This is our current ecosystem. So we have our Neo4j native graph database there in the upper left-hand corner. That kind of gives us a good point for our data, analyzing our data, putting it in and out, and retrieving it. It's stored as a graph, so nodes and relationships, and then you can traverse those paths. Then we add the Cypher query language. That helps us kind of query data or put it in or take it out, et cetera. But you can use that to kind of traverse the graph and kind of do some basic analysis. And then we added APOC procedures on top of that. So this does things like aggregations, data cleanup, import, export, all kinds of different things. Anything you could possibly imagine is probably in APOC. And then we added graph algorithms on top of that. Graph algorithms this library is optimized to run on Neo4j, so it utilizes all the powers and optimizations that we've built into Neo4j. This library is specified for that, so it works really, really well and very performant. And then we have a ton of integrations. So anything you're running, vendor tools, front-end analysis, BI, et cetera, all of that stuff can interface. So we can plug into a lot of those different things and pipe those results of those algorithms pretty much out to anything you could possibly want. So how do you actually do this? You'll call it as a Cypher procedure. You'll pass in a specification, use like a label or a property or a query, as well as some configuration, and then you can execute and return the results back. So there's a stream variant that'll give you just a ton of results. It's almost like seeing a massive log file of results come back to you. But if you don't want to look at all that or you don't want to sift through all of that, you can also do a non-stream variant, which basically writes the data to the graph and then just returns statistics on that. And then you can query that at your leisure. One last thing before we dive into our demo is I want to talk about Cypher projection. This is a really neat feature that allows you to do kind of some what-if analysis. So it basically allows you to overlay a subgraph structure in memory, run some analysis on that, and then take that subprojection off without changing that data underneath. So say, for instance, I had a list data of drug results, and I wanted to see how it made a difference between men and women, but my graph wasn't partitioned based on gender, and so I could actually run Cypher projection to say overlay this partitioning structure and say for these two genders, look at them, analyze them, run my queries, etc., and then take that projection off, and nothing about my underlying data has changed. So you can see how this could be really useful for running tons of different what-if analysis scenarios. Say, what if my data looked like this? What if it looked like this? What if it was partitioned this way? And run your queries and your analysis, and then go back and you're not writing anything to the database. You're not changing it. Okay, now it's demo time. This is one of my favorite demos, too. Okay, so for those of you who are familiar with, oh, that's helpful. Sand dune, a massive sand dune. Much better. Okay, for those of you who are, you know what I probably should do is, I normally mirror my display on this. Not helping. That's why I normally mirror my display. Voila. Okay, much better. Now I can see it and you can see it, so I don't have to try to type like that. Okay, so for those of you who are familiar with the Game of Thrones data set, this will be basically validation for you. So you'll start seeing some of the results of this analysis, and you'll go, yeah, these results totally make sense. If you're not familiar with this data set, don't worry, I won't throw you out of the room or make you stand up in the middle of the group or anything like that. But what this will show you is the power of what these algorithms can do for you, can show you. So without ever cracking a page of the book or watching the TV series, you can understand the connections, the influence, the important characters, the plot lines, etc., throughout the entire series. So both sides, you'll hopefully get something good out of this. Okay, the first thing I want to do actually is show you the schema that we have in the database. So we're just going to look at, this is a relatively simple data set, and that's okay. I still think it's actually really cool that you can see as much information as we're going to see with such a simple data. But if you look at, we're just going to look at characters, and then we have 4 different types of relationships. So we have an interacts 1 relationship. That's for character interactions in book 1. An interacts 2 for characters who interact with other characters in book 2. Interacts 3 for book 3, and then interacts 4, 5 for books 4 and 5 taken together. Not quite sure why we had actually a community member do all this analysis and put it into nice flat files for us. I'm not sure why he grouped 4 and 5 unless it was right after 5 came out and he just threw them all in one. But he also has separate files out there too if you're interested. So we have all this analysis. We're just going to focus in on this. So what I did up here, I'll go ahead and unpin that, is I just loaded a browser guide. Oh, no. Oh, I'm in incognito. No, that was working earlier. I'm not connected to Wi-Fi. Why am I not connected to Wi-Fi? There we go. Okay, let's try it again. Voila. Okay, it's amazing. Wi-Fi makes everything work. So I have this browser guide out here. The first link on this browser guide is just going to kind of show you the data. It's going to show you the background, what the community member did to analyze all this, et cetera, help you get it loaded. But I've already done all that. So I'm going to go on to the second one, which is going to do some of the analysis and kind of deep dive on this. So just basic overview. So we're going to skip on to our betweenness centrality. Now remember I talked about that this looks at the bridges. What are the nodes that are the bridges between different clusters? So what we're first going to do is we will look at betweenness centrality for characters. By the way, can everybody in the back see this? Or do I need to zoom it up? Okay, cool. We're going to look at characters, because that's all we're dealing with at this point. And then we're going to just look at the interacts 1 relationship. So we're just going to look at character interactions in book 1 only for now. And we're going to look at both direction of the relationship. We're going to pull back our node ID and our centrality. We're going to match characters where the IDs match, of course, and then return the name and the centrality, order by centrality in descending order, and then just pull a top 10 out of that. So basically what we're doing, we're just looking at the top 10 highest central characters or most influential characters in book 1. So for those of you who know the series, this list probably makes a lot of sense. For those of you who aren't familiar with the series, you now know the most influential and important characters in book 1. So Eddard Stark tops that list, may or may not be surprising to you, followed on down. Now it's really important to know what you're asking of your data. So in that one, we looked at betweenness centrality. What's the influence? What are the bridge nodes? However, what if we looked at maybe the people who know the most groups, maybe they don't have the deepest relationships. Maybe they don't communicate and form deeper connections with these people. So what we're going to look at here is who are our biggest communicators versus their centrality scores. So we're going to call that algorithm package, algo.betweenness. So that's our betweenness algorithm. We're going to stream the results back. We're not writing anything to the graph. Remember I said you could either return the results as a stream or write results to the graph and return that later. We're going to do this as a stream. Again, pulling characters, interacts one relationship in either direction. Pull back the node ID and the centrality, and then match characters. And then look at the name and the centrality. Look at the characters interacting with other characters, call those interactions, return those back, and then basically we're just going to look at who were the characters they interacted the most with. So we sum up the total interactions and then look at the characters they dealt the most with. And then again, ordering by centrality and pulling out that top 10. So it looks a whole lot more complicated than what it is. But basically, the first two columns on the left-hand side are the exact same as what we saw in our last query. It's the two columns on the right-hand side that we've added. So you can kind of start comparing. Notice that the ordering of this list is exactly the same, because again, we're ordering by centrality, and then you can start comparing the interactions on the right. So Eddard Stark still tops that list. So okay, he ends up important yet again. And then following on down, but where it gets interesting is if you look at Tyrion Lannister and Jon Snow. So Tyrion has a higher centrality. He groups and bridges more groups of people. However, Jon Snow has more interactions than Tyrion does. So he has more communications, more conversations, maybe he writes more letters, maybe he interacts with these people more on a deeper level, and he has better friends or closer friends than Tyrion might. And this kind of propagates on down the list. So if you look down at Brandon Sansa Stark there at the bottom, they have a really low centrality, so they don't bridge very many groups of people. However, they have higher total interactions than Catelyn Stark does up above them. So they form deeper relationships or deeper friendships than probably what Catelyn does. So what we've done up until this point is, you saw we executed the stream. We've executed all these results on runtime. So every time I hit that little play button to execute the query, it's actually calculating centrality each time, returning the results back to me. But if you had a really massive graph, you may not be able to do that, or you may not want to stream all those results back. So you can actually store the centrality as a property on the database and then just retrieve that at will. So I've already done this, so I'm not going to run that particular query. But I am going to go ahead and return the book one betweenness centrality on the property. So this list, the return result looks exactly the same. I'm just pulling from that written property versus executing on runtime. So mostly the same, the execution's different. Okay, so let's expand this a little bit. We've already talked just about book one. Let's kind of extend this out and look at the rest of the series, or the current series as it stands. I'm hoping for the next book. We'll see. I've already stored betweenness centrality. So now we'll just look at the increase in influence over the course of the series. So we'll start at book one. We'll see, okay, who are the highest or pull everybody's betweenness centrality, pull book 4-5 betweenness centrality, their centrality at the end of the series, and then subtract book 1 from book 4-5 centrality numbers, call that difference, and then order by the differences and pull the top 10 of those out too. So throughout the entire series, who were the most that grew in centrality throughout the books? So what you're going to find, Stannis tops that list. So we started at very, very low centrality at the beginning of the series. He was hardly mentioned in the books, but by the end of the series, he becomes a very prominent character, groups a lot of nodes and clusters together, and so he grew the most throughout this current series. Cersei Lannister comes in right behind him. She had a higher book 1 betweenness centrality, but she also grew quite a bit by the end of the series, and so she kind of ended up close there at the end. What would be really interesting here is to actually look at kind of insert books 2 and book 3 centrality scores here in the middle, and kind of see if you had any characters drop off all of a sudden and then come back through the story. So see how George R.R. Martin kind of tended to weave his stories in and out. Maybe there were characters he focused on more in one book than others, etc. And I've actually done some of that analysis. It's actually really interesting. So not just looking at the bookends of the series, but then looking at as a course of progression. I will not run this query because I don't want to spoil anything for you if you're not familiar with the series. So as you can probably imagine, if you run decrease in influence, who decreased the most in influence from books 1 to books 4, 5, and you see a character that all of a sudden drops off, probably not a good sign. So if you're familiar with George R.R. Martin's writing or heard rumors, you know that he has a tendency to kill off very dear and beloved characters. And so running decrease in centrality will kind of give spoilers for you. I made the mistake of running that when I was in the midst of book 3. I was like, oh no, now I know, who's already dead and who's going to die. So not too good on that one, but you're free to and welcome to run it at home at your own leisure if you want to know or if you already know, etc. But kind of interesting. I won't do it in public and run anything for you. So now we can look at consistent influencers. So we can look at who was really high centrality at the beginning of the series, who was really high centrality at the end of the series, and see how much consistency. So basically what we're going to do is we're going to take the top 10 from book 1, we're going to take the top 10 from books 4 and 5, we're going to overlap those two top 10 lists and see, are there any characters that exist on both lists? So that's basically what this does. Matches characters, orders by book 1 between the centrality, pulls the top 10 out. Then it's basically going to collect those together into a list and then match more characters, pull the book 4, 5 between the centrality, order by centrality, and pull the top 10 from books 4, 5. And then it basically does an intersection of those lists and sees what are the characters that exist on both. We're going to limit to 10 because we could potentially have 20 different characters. But we only end up with 4. So these 4 are the ones that were on the top 10 in book 1. They're still on the top 10 in book 5. Again, you could run some analysis to see between books 1 and 2, between books 2 and 3, between books 3 and 4, and 4 and 5, et cetera, and then over the course of the whole series. So you could do a little bit more fine-grained analysis on this. The query gets a little complex, but it's a lot of fun and very interesting. So this just shows you that these characters, they are still alive, end up being heavy influencers throughout the course of the series, at least as is current. Page rank. So I mentioned that this was a little bit different than between the centrality. The reason for this is you get some of your neighbors' importance. So if you're connected to some very important people or some very high up people, you kind of get some of their page rank as well into your score. Between the centrality does not do that. So if I were to query PageRank, I'm going to look at characters. Basically, I'm also going to sum up the interactions here, total them up, look at the characters they interacted with the most, and then just pull book 1 between book 1 PageRank, and then order by top 10 and just pull those out. So I'm going to look at the top 10 page ranking. Eddard Stark still tops the list. Good grief. So he's still high up on all of our scores, so he probably is a very important character. But as you start looking down the list, this is where it gets interesting. So if you remember right, Robert Baratheon was our second tier on our centralities and on some of our other measures. But Tyrion actually takes the cake on page rank in second place here. Even though his centrality score isn't quite as high, his total interactions isn't quite as high, but he's connected to some very important people. Some very wealthy, some very prominent people, and so therefore he gets a higher page rank. Another one that's really interesting is right below him is Catelyn Stark. She has a relatively low, between the centrality, total interactions, etc. She's not like a main character in that first book, but she's connected to some very important people. Eddard Stark probably helps her page rank quite a bit. And then she's connected to some other very important people as well. So then you have Robert Baratheon and on down the list there. But notice that also Jaime shows up on that list, and he did not show up on our centrality score at all. So interesting there. A little bit of a different perspective. Now we're going to look at community detection. So this is just going to run a label propagation. So if you have kings and knights that tend to work together, it's going to kind of propagate some of these labels across and just kind of see what kind of tends to be our communities. Who does George R.R. Martin tend to focus on? And basically, how does he construct and organize his fantasy world that he's created? So if we run this, again, I already ran the storing the query in the database, so I'll just actually run and pull the results back. So if you see this, you can see that he has basically one pretty large community that he tends to focus on, so kind of one organization of his plot, and then he has a few kind of medium, small-ish communities. By the way, on the left-hand side here is our community ID. It's just the number, and then on the right-hand side is the size. So that's the number of nodes in that community. Sorry, I didn't explain that. So he has one really large community there, and then some kind of medium-ish ones here, and then tons and tons and tons of small ones. So we kind of have some one-off communities, but then he focuses on a main one as well as having a couple of outliers he kind of probably weaves into the story some. Then you could start combining some of these algorithms. So you can look at influential people within each community. So you could calculate page rank with communities. You could also look at the interactions between people in a particular community. And in this case, you can look at page rank within the second largest community. So you could pick a particular community and say who is the highest page rank in this particular group. So you could start kind of breaking this all down, looking at influential characters, etc. So there's tons more analysis that can be done in this area. You're welcome to do this at your own leisure. In fact, I'll show you some ways that you can do that. But in the convenience of time, we will sadly move along. So back to this. This is a visualization done on the graph data we just looked at. So this was done using neoviz.js. It is an open source library that my colleague Will Lyon created. Very cool, obviously does a lot of really neat things. But it's really easy to plug in graph algorithm analysis and kind of those values. So based on the size of the node, that's betweenness centrality. So the larger the node, the higher the betweenness centrality. The thicker the relationship, the higher the page rank. And then the colors represent the different communities that are represented in the graph data. So you can see how the visualization would give you just a very quick visual overview of what's kind of existing in the graph, maybe what you might want to focus on. So there's a ton of really thick relationships and large nodes here. Maybe you want to focus in on that group and kind of pull apart and delve deeper into kind of how they're connected and why. Or maybe you'd want to look at Daenerys' community over here and start analyzing the connections there and maybe the few relationships that are across into other communities. Like I said, you can do this analysis all on your own. We have Neo4j sandbox instances that are relatively spread out use cases. There's pre-populated data sets you can use, as well as being able to import your own. But all of these sandboxes here on the right-hand side automatically have graph algorithms installed, as well as I think our blank sandbox might as well. That's one you can just import whatever data you like. But yes, all of these have algorithms, so you can use the data set that we already give to you, and then you can run your own analysis on that data. You can also, so this doesn't require a download to your local machine, it's all online. It'll spin up an instance for you, and you can run data and import queries and things like that at your leisure. However, if you do want to download to a desktop, we do have an application that you can just install graph algorithms with the click of a button. You can run local databases on your computer, your laptop, etc. And then just at your leisure, start and spin down, et cetera. Our sandboxes do have a expiration date. This would not, but whatever is more comfortable for you. We have some various data sets you can use. So I ran the Game of Thrones one, relatively small today, but we also have Yelp business graph data that you can use. There's a ton of demos and blog posts and such out there for that. So if you need help or questions or anything like that, there's good resources for that. We also have a Neo4j community graph, so everybody that's in our Neo4j community, you can access some of that information and run some analysis there. And then we have a DBpedia example, which is pretty large. And then my colleague also has a Bitcoin example, but that one is several billions of nodes and relationships, so it's kind of unwieldy to run in a demo like this, but we do have the resources for that, so feel free to reach out if you're curious. My colleagues are releasing a graph algorithms book, so it does both examples on Neo4j as well as in Apache Spark. So if you're interested in something like that, that is on pre-order on Amazon right now. It should be released, hoping sometime this spring. So if you're interested in that, feel free to go out and check that out or get a pre-order. And then we also have some resources. So we have our Neo4j community site. You can ask a ton of questions out there based on anything. We have a section on graph algorithms, but there's other things too. Our YouTube channel has a lot of videos and walkthroughs and tutorials and things there. GitHub, our Neo4j graph algorithms library is open source, so it's out on GitHub. It's a Java library, but you can basically just package it up and throw it in as a plugin with Neo4j. It's pretty easy to use and just extend that. And then we have white papers as well as other documentation. Our new docs are out on our website. We have a separate section for graph algorithms now, and other information out on our website, of course. So feel free to contact me, email, Twitter, etc. However you feel you can get a hold of me. We are happy to answer questions, talk at leisure, help you work on solving problems. So thank you very much, and enjoy JFocus.